Okay. So again, thank you everybody for coming today for Erik's Defense. So we're really proud to present you the work of Erik's 2.5 years with us. So Erik joined UVM right after the pandemic, coming out of times that quantum computing startup, teaching mathematics, so super interesting background. He came with very strong ideas about computer complex systems, and you will see that these ideas have become even stronger during his 2 years here. He was super appreciated by the program, ran the Scraps kind of seminar for the students for a year, also contributed greatly to the joint labs of science. As you will see, the science is far reaching. It's really a shame that theses are only a fraction of the work that go into a final product. Erik has put out an amazing number of results over the years, and this is a simple distillation of most of this work in written form. So with that, I will give you the floor.
Great. Thank you so much, and thank you all for being here. Thanks to the people online. I'm super excited to be here and talk about my work on robust interventions in network epidemiology. And before I do that, I just wanted to start with a story about when I first came to UVM. As some of the people in the room will know, I was incredibly excited about complex systems. It was like the middle of COVID, and I'd just been reading papers and just being like, oh yeah, I mean, these models can describe the entire world really accurately. And in my head, when I came here, I had a very clear idea of the kind of research I was going to do. And it went something like this. Something like this. Okay, so this was my image for how we were going to solve all the world's problems. It started with building a model, right? And because it's complex systems modeling, we can represent all the intricacies of all the way that everything in the world depends on everything else. And so you build a model of the system you're interested in. Step 2 is you understand how the model works. What are the key drivers of the system? You figure out the methods. Step 3, you figure out what's the best way to change the system by tinkering with your model, figuring out how you can get the model to produce outcomes that are more desirable. And once you've done that, it's job done. You just ship it off to the President of the United States, and then that's probably taking a few hours, and then you go to lunch. There's a lot of giggles in the room because it's like ridiculously naive, but it's like how I was thinking. All of this is just so much more complicated than I had originally let on. But that didn't stop me thinking about this as just sort of a broad framework for how we could potentially use complex systems to produce insights and make better policy decisions. So just like a simple example of where I learned how bad of an idea that framework was, first semester in a class, I was building with some others a model of the housing system, and I was interested in how COVID would change where people wanted to live. People wanted more space, they could work from home, and you would untether lots of previous constraints that existed in the housing market. So basically, we built a model with some locations, and there's some people, and they moved around to maximize their preferences for housing. And then you would have these outcomes of the system. You had where people were living at every time step, and then before and after COVID happened, where people were flowing in and out of, average cost of housing. And we never really got to interventions, but assuming we did, we'd have some knowledge. I mean, who is going to listen to this model? What do you do with that? You have all these outputs of the model. How is that actually useful to anyone? And I think the crux of it for me is, how do you actually know that your model is right? How do you trust it at all? And what is the role of models in our decision-making process? And one way to build confidence in these models is to try to learn them from data. And that's good, but it's really hard when you have so much complex interdependency that we want to deal with in these complex systems. You can also just trust your human expertise, which is also good. We should trust the people who are building models. But that's always going to have some bias in it. And then, we could also just scrap the whole idea of building models that represent the world exactly and using them for decision making, and just say, listen, we built a system. It doesn't necessarily have to be exactly like the world, but it'll give us some intuition for how the world works. And so, on all of that, maybe you'd ask the question, what if you did use models for decision making? What would happen if you screwed it up? If you built a model that's not exactly like the real world, and then you intervene in the world, and then something goes wrong. And so it kind of boils down to what happens if you get your model wrong, and then could you come up with an intervention according to your model that works for lots of different situations? You're not sure what the real world looks like, but you have a range of possibilities, and you have this so-called robust solution. So today I want to talk about the application of these ideas, big ideas, to a very specific problem. And that's the spread of disease on networks. And so what I'll do is first introduce these models of spreading on networks, and then discuss 3 decision-making contexts for how you might intervene in this spreading system. Then there's a bit of a detour about calculating the potential quality of interventions analytically using this technique called message passing, and it'll make more sense when we get there. And then we'll just look at outlooks for the future. Okay, so models of the spread of disease. The basic workhorse of spreading models is the SIR model. And the basic idea is you have lots of individuals in a system, and they're potentially able to be infected with the disease. So they initially start out as susceptible. There might be one or a few individuals in the system that are initially infected. And then through interactions with each other, these interactions will allow the disease to spread from individual to individual. And then for infected individuals, they'll eventually recover. And Juniper can be co-hosted if you want. These individuals will eventually recover, and that's basically the pipeline. And once you're recovered, you can't be infected anymore. And why networks? Well, we don't actually interact randomly with other individuals in the system. These interactions are very structured. And networks just provide a very general mathematical data structure for describing who's interacting with whom in the network, in the system. So, in our real lives, we have our friends, we have our colleagues that could potentially infect us, but not someone who lives out in California. And so that's what the network does. And these models apply not just to epidemiology, just so we're not constraining ourselves too much. Cascading failures in financial markets, supply chains, the spread of information it makes sense. You have a meme that gets retweeted on Twitter or something. Opinions and behaviors is a bit more tentative. You're better off with a more complex model than what we're going to use here. And then, of course, the spread of disease. Okay, so the specific spreading model we're going to use in this work is the independent cascade model. And it's related to the SIR model under a certain set of circumstances. If you and the relationship happens through this mediating process called bond percolation. And bond percolation comes from statistical physics and originally studied in the context of fluids flowing through porous rocks. But here we can use it on networks as well. And the process is very simple. You filter a bunch of edges from the network, and you only keep each one with a probability p. And when you keep an edge, that signifies that the disease could have spread along that edge in the network. And so it's exactly equivalent to saying, okay, an individual is infected with each of its neighbors in the network, it will infect them with probability p. That's the model. And this infection rate really matters. When the infection rate is low, you end up with just a few edges in this percolation process. And so you could say, okay, I pick an individual at random, and if there are any red edges attached to it, you could follow them and infect those people. And then all the way for high infection rates, high P, you have lots of percolated edges in the network. And so if I pick this node, it would spread through across all of the red edges. And in the middle, there's this interesting thing that happens. We'll call it a critical threshold. If you're a statistical physicist, turn away, because this is not a rigorous definition of what that means. But effectively, the idea is for low infection rates, you're not likely to get a very large outbreak. And then at a certain point, you're suddenly likely to get large outbreaks. And that critical threshold will become quite important. And we'll denote it by phi, which is just the infection rate over the critical threshold. So phi equals 1 corresponds to right on it. Okay. Now let's look at interventions in spreading processes. And we'll think about 3. The first is a traditional problem from the literature, and it's called influence maximization. And it was first studied in the context of viral marketing, where you want to sell a product as widely as possible, and you expect that people who buy the product will share it with their friends. And so you want to advertise to people in the network who have lots of friends who are very well connected, so that you can maximize the sales of your product. And so that's effectively it. You pick K seeds of the contagion. And what I'm plotting here in the blue is the probability that each of the other nodes becomes infected on average. Okay, that's what that pi I represents. The second problem is sentinel surveillance, and this applies more specifically to epidemiology. And instead, what we're going to do is monitor K nodes, and we keep monitoring them so that when an outbreak does occur, we want these nodes to, when these nodes become infected, we'll be aware of an outbreak. And so we want to minimize the time to infection for this set of K sentinel nodes. And here you can see around the sentinel nodes, each of these neighbors are more likely to be infected on average. And lastly, probably the most intuitive problem is vaccination. You vaccinate nodes, they cannot spread the disease anymore. And you want to pick nodes such that the overall outbreak size is minimized. More generally, you could just think there's some spreading process happening, and we specify, some inputs to the model. We have these dynamics. We specify the infection rate. We specify the graph on which things are happening. We specify, and then we run a bunch of simulations, and we generate this distribution of possible outcomes for the system. And we can evaluate that distribution in some utility function. Each outcome has some value, whether we'd like it to happen or not. So vaccination, we want the number of total infected people to be as small as possible. And then we can optimize for these the decision parameters. And just to formalize things a bit, we'll call a problem instance a combination of one objective function and a dynamical set of dynamical parameters. In this case, there's just one, it's P. And together, that fully defines the optimization problem. And so for any given intervention, the dynamical importance of this set is this function Q, the expected utility. And it's actually difficult to calculate exactly because the possible outcomes for the system is huge. Each node could be either infected or not infected, and it's this sort of bit string expansion. So you have 2 to the n possibilities, and it's impossible to calculate the probability for all of them. So what we'll do is just resort to Monte Carlo sampling. You effectively just run a bunch of simulations and calculate the probability on average. Or you could use message passing, which is something we'll discuss next, as a way of more efficiently computing this quality. Okay. And as I said, it was an optimization problem. So you take the set that maximizes this function. And that too is a really difficult problem. The number of possible instances is n choose k, and that's too big to explore every possibility. So what we use there is a greedy algorithm. The way that works is you pick the best first node and then add the second node that works best with the first node, and so on and so forth. Okay, so now that we've set all that up, the idea will be to for each objective function and over a range of infection rates, we'll take the optimal set, and then we'll evaluate what happens if we were to get the wrong, if we were to optimize for the wrong thing, and then we could potentially lose performance. Okay, so you have a true underlying objective function in the system. You have a true set of a true infection rate, but you think the infection rate is something else. How much performance do you lose if you optimize for the wrong thing? So we'll start by looking at influence maximization, and on the horizontal axis, it's the infection rate for the true problem, and the vertical axis is the infection rate for what you assume to be the case. And just kind of working from left to right, when the infection rate is really low, there's no real outbreak happening on the system anyways. And so no matter what you do, you're not going to really lose any performance. But as the infection rate increases a little bit, suddenly, if you assume the infection rate to be really high, and that's that top left of the plot, then you're going to lose a lot of performance. You lose a lot of expected utility. On the other side of things, if the true infection rate is really quite high, and this is the bottom right, but you've assumed the infection rate is low, you're also going to lose performance. So you have these two regimes, the sort of supercritical regime and the subcritical regime, where if you don't get that right in terms of the infection rate, you'll lose performance. Things are a little bit different for vaccination. It's a little bit less symmetric in the sense that anything subcritical, there's really no performance loss at all. No matter what you do, there's not going to be a large outbreak spreading in the subcritical regime, so you don't lose any performance. However, if you assume that the infection rate is quite low and it's actually quite high, there's some performance loss as well, and we can talk about in a second why that is. And similar story for sentinel surveillance, actually, kind of exact same as vaccination. Okay, now, instead of thinking about misspecifying the infection rate, what happens if you misspecify the objective function? And that might seem a little bit weird, like I know what I'm optimizing for if you're trying to intervene in a system. Why get the infection, the objective wrong? But it's really more like, how much does the optimum set from one problem translate over to the other? If we think about a situation where you're doing some kind of contact tracing, you want to find good sentinels to be aware of outbreaks, but then a vaccine becomes available and you want to say, okay, can I use the people in my contact tracing system as good choices for vaccination? That kind of thing. And what you see is again this dependence on the critical threshold. So for low values of the infection rate, you don't actually lose, like no matter what you do, what thing you optimize for, you're not going to lose all that much performance. But then for higher levels of the infection rate, you do. And the story is roughly similar for all three problems, except you can note that influence maximization does really poorly on vaccination and sentinel surveillance in this supercritical regime. Okay, and so now what happens if you put it all together? You have this full uncertainty. You might potentially get the objective function wrong and also get the infection rate wrong. And just here is just kind of all the information all at once. You've already seen these diagonal plots. That's comparing within problems. But then the rest of these off diagonal plots are what happens if you misspecify the problem and the infection rate. And I'll just sort of note two things. The first is the supercritical influence max sets are really awful for the other problems. No matter what infection rate you assume, if you're assuming vaccination or sentinel surveillance, there's just this big blob of purple to show you that if the real problem, the sort of true problem, is supercritical influence maximization, none of these other sets are going to do that well. And then we can look across the entire space of true problem instances. And you can also see that if you assume that the problem was supercritical influence max, there's this the same thing. You're going to lose performance in vaccination and sentinel surveillance. The second story is that for vaccination and sentinel surveillance, they're quite similar, right? Compared to influence maximization, the roles of these things are roughly the same, and that's useful knowledge, really. The last question, and you can sort of decide for yourselves, is what out of if you had to optimize for one thing that you wanted to do well across the entire problem, which sort of problem instance would you optimize for? You know, where along here would you pick so that you'd expect this sort of you want to have yellow all the way across, and that's sort of a set that's general or potentially robust. Maybe that it's kind of yellow here and yellow here. I mean, if you squint, that's around this critical point. You might have a set that kind of is a quasi jack of all trades. So what's actually going on with these sets? We can just kind of dig in a little bit. I'll just show the optimal sets for a few infection rates. For influence maximization, you see that kind of at the critical threshold, you pick nodes that are roughly distributed through the main clusters in the network. And then as you increase the infection rate, you see that the optimal sets start spreading out to the periphery of the network. You start picking, for instance, these extra clusters. And that's because you know that you're going to get a really big outbreak no matter what. You don't need to load up on lots of seeds in the center core of the network, and then it becomes about picking peripheral nodes to maximize the reach as far as possible. And I think this is like a good way to contextualize why it's important to think about dynamic importance as to just what's important about a node in the network in terms of just the structure of it itself. And this is a very weak analogy, but like you have an election and you know that the core of your base is going to vote for you no matter what, but then right around the boundary, that might decide the election. And it's a sort of different definition of what's important when you take into account the dynamics of the system. Okay, for vaccination, completely different story, really. The goal is to kind of break up the major core of the network so that you don't get a big outbreak. And as the infection rate increases, put more nodes into this core to break it up. And this kind of explains why if you assumed the infection rate was too low for vaccination, you would some performance because you didn't put enough nodes in the core of the network. And pretty much a similar story for sentinel surveillance, actually. That these actually not a similar story. These look roughly the same. It's kind of hard to suss out what's going on for sentinel surveillance. So we might ask ourselves, how similar are these sets actually? And that's the last thing we'll look at is how to compare the optimal sets across all these problems. And we use this similarity metric. It's based on harmonic distance in the network. So you try to find a matching between two different sets such that the distance between the mapping, this bijective mapping, is minimized. So if you have these, set one, set two, three of the nodes are the same in both sets, and then you have this fourth set where the two nodes are different, and the distance between those two nodes in the network will determine whether these two sets are very similar or not so similar at all. Okay, so let's look at influence maximization and see how similar these sets are. And you just see this very clear, stark transition between the kind of sets that are good for subcritical regime and for the supercritical regime. And you don't really see that for the other two problems, which kind of explains why these supercritical sentinels or supercritical influence sets are so different, are so bad across all these problems. Okay. You can also look across problems, and again, you see that these supercritical influence sets are just completely different from everything else in the system. And I think it's interesting to see too, sentinel surveillance versus vaccination, they're most similar in the subcritical regime too, but broadly are roughly similar or close to each other in the network. Cool. And then just to wrap up on this section, a few methodological details. We use this fast algorithm to compute percolation from Newman and Ziff. It's very fun, but it's quite efficient. And we modified it further so that you could compute the quality of lots of sets in parallel. And so I just want to go off the impression that the code isn't inefficient as far as we know, but it still took quite a lot of time to compute just to run, say, the best set for sentinel surveillance. For these higher infection rates, it would take 36 hours on the VAC or more, and that's a long time. So you couldn't necessarily do larger networks reasonably well with that kind of method. So we were thinking to ourselves, could we use something faster to test these sets more efficiently so that we could run that study on larger networks? And so now we'll come to the second portion of the talk, which is message passing. And the goal here will be to use message passing to calculate the marginal probability that a node is infected. Okay. And that's basically, you have a lot of outbreaks happening at random. They start from a random location, and then you look at node I and say, how many times out of all the possibilities has it been infected? That's the marginal probability. And so if you have that for every node, you can actually calculate the full outbreak size. So that's useful. And from the full outbreak size, that's a quantity of interest that we can use to evaluate the quality of these interventions. Okay. There's also some message passing, some parts of the literature that do what's called dynamic message passing. And the idea is if you choose the initial conditions of your system just right, you can actually compute the full temporal marginals of these probabilities, and that'll be useful for sentinel surveillance where you really need to think about time. There's one more piece that we've sort of roped in here, and it's message passing, or message passing traditionally only works on trees or tree-like networks, and so we've roped in this method that expands the framework so that you can account for networks with loops, like the network we just used. Okay, so I don't have time to go over all of message passing right now. It's a bit finicky, but I'll just sort of give you a few basic ideas of how it works. And you might start by thinking, okay, you have the infection status of a node is this random variable, and then you have the marginal. And you can say, well, actually, the only way that a node can be infected is through its neighbors. So if I somehow knew the probability that my neighbors were infected, I would know the probability that I'm infected. And just here's a diagram of how you could calculate that. You could say, okay, I'm 2, 1, 4, 5 could have potentially infected me. And assuming I know the probability that 1 was infected, then it's just P times that they infected me. And then this quantity is just the probability that at least one of those things happened. And you say, okay, each one could independently infect me with this certain probability. Okay. And you don't actually know, the problem is you don't actually know the marginal of your neighbors, but if you're able to build out a system of equations that relates all of the marginals to each other, what if you could pick some initial values and then just iterate these equations to convergence, and then the system would converge to some value, and that would give you your answer. And that's what we're going to do. Unfortunately, these equations, the one I just showed you, doesn't actually work right out of the box. And there's kind of two problems with this. Is just a simple network, and I've implemented those equations on here. The problem is twofold. The first is I set the initial values to be 1 over n. Each node has initial probability of being infected to be like 0.14. Okay, and then you iterate the thing to convergence, and you find that in the long time, all of the marginals go to 0. So clearly that's the wrong answer, because at least some nodes were infected some of the time. So the first problem is that you need to sort of handle the initial conditions better. And we'll do that. We'll fix that. But there's also another problem, which is you can look like the green's going up and down and up and down and up and down, and the red's going up and down. And they seem to be kind of cycling through each other. So when 2 and 3 are really, the marginals are really high, then on the next step of the algorithm, 1 will be the marginal of 1 will be really high, and then vice versa. So it seems like the nodes are infecting each other, which is kind of weird and not very physical. So we kind of need to fix both of those problems. And we can do that. The first is we come up with a new variable, which is the probability that each node was initially infected. And we'll let that be SI. And then we'll say, what's the probability that I has been infected by a node other than J, which is, you should tell me the probability that you're infected, but exclude the fact that I could have infected you first. Don't tell me that, because then we'll be passing messages back and forth, and that's going to be not great. And so if you fix it, here's the equation you get. And you can see that the message now is, okay, I'm 2, and I'm going to send the probability that I was infected, but I'm only going to include information from 4 and 5 because 1 is the person I'm sending my message to. So you have this new system of equations, and when you implement those, ta-da, everything works great. I'm not plotting the marginals, but here's the outbreak size. There's message passing, simulation, you converge to the right value. Job done, as long as you're dealing with the tree. On loops, it doesn't work so well, as you can see. And so we kind of have to figure out what's going on there. And just to give you some intuition for why message passing is overestimating the true value, just show you what the messages look like for a few on the in the system. This is the message 1 sends to 2 is the probability it's been infected by a node other than 2, but that includes 3. And then the message 2 sends to 3 includes 1, and then the message 3 sends to 1 includes 2. So you get this cycle where effectively 1 sends a message to 2 and it goes, and then it comes back to 1. And that cycle will cause you to overcount in the system. And it could also happen elsewhere. So, when you have lots of loops in the network, you're overcounting a lot. Okay. And so now it all starts to get quite complicated, but there are ways to mitigate the effect of this overcounting. The idea is you define a neighborhood, a region around node I, that you're going to take care of all of the loops explicitly within this region. And the hope is that it's the short loops that really cause your algorithm to overcount. And so you define these neighborhoods, and then you can have these messages that say something like, okay, what's the probability that 2 has been infected, not just except for 1, but except for all of the nodes in the region of 1. And then you calculate the probabilities explicitly from there. I won't go into any more detail than that, but that's the gist of the method. And you can construct these neighborhoods of kind of arbitrary size. So we'll have this R parameter, and R corresponds to how big your neighborhood is. So R equals 0 is just normal message passing. You only include the neighbors. So that's this B figure down here. And then R equals 1 corresponds to C. You have a loop of size 3. And R equals 2, you have a loop of size 4. Okay, and then you can add interventions to the system, and I'm just going to flash through these. We can't go into all the details now, but effectively you set the seed probability for influence maximization to 1 for the seeds. For vaccination, you set the infection rate for specific edges to be 0, so that certain nodes effectively can't, the vaccinated nodes can't infect anyone else. And for sentinel surveillance, you employ this dynamic message passing thing, and you can calculate the probability that a sentinel has been infected. Okay, so I'm not going to show you all the results. I'll just show you for the problem of vaccination. And And again, we're going to use this Facebook Friends network as 362 nodes. And we'll pick 20 random seed sets of size square root of n equals 19. And then the last few intervention sets that we'll test are the highest ranked nodes according to some different centrality metrics. So the highest 19-degree nodes, or the highest 19-degree nodes in the network, etc. Okay. Here we are. That's the result. We computed the quality of these sets according to message passing and according to simulation. And here's what you get, really. At the critical thresholds, you can see that taking into account these neighborhoods actually gives you a much better estimate. R equals 1, 2, and 3 all give you quite good results. Which is surprising because I mean this network has a lot of loops, right? And then for higher infection rates, you start to see some problems. R equals 1 starts to struggle at 1.5, and then kind of all of them start struggling at twice the critical threshold. And overall, you can just see that message passing will eventually overestimate for high enough values of the infection rate. But we have done better, right? Taking into account neighborhoods, you improve things a little bit. So maybe you can use message passing to compute the qualities more efficiently than just doing simulation. And if you think about that robust solution that was kind of around the critical threshold, if you wanted to optimize for that on a very large network, maybe including neighborhoods gives you enough of a postponement of that overcounting to give you better results. Okay, so that's basically the bulk of the thesis. This section we introduced the message passing method to calculate interventions for all of these problems. And now I just want to zoom out a little bit at the ends and talk about big ideas again. We've huge ideas go to small and then back to big. How you could employ this framework elsewhere. As I said before, all you really need for these problems is some dynamical model, and then you could classify the model as having some input variables, some decision variables, and then you need some utility function for the outcomes of the system. And if you have that, you could, in theory, design some optimal interventions. I'd be kind of curious to see what happens if you plugged a voter model in here. You have these things called zealots, and they don't change their states, and maybe optimally placing zealots might be some of these problems. I'd be curious to see. Complex contagions is another thing where I think the seeding strategies would be quite different. So I'd be really curious to see how that goes, and then any other dynamics we can think of. There's also a notion of, beyond model misspecification, we could compute what it would cost us if we got our parameters wrong. But we could also say, okay, we don't actually know. We don't have to pick one single value. We could maybe optimize over a distribution of values. And so say you had some data, you could infer some posterior about the input parameters of your model. You could calculate, you could come up with some Bayes estimator for what is the optimal robust set in these scenarios, and that would be a sort of formal decision theory type thing. We haven't really at all touched on what happens if the true world isn't even in your model class at all. You write down a model and the way you parameterized it is completely wrong. The dynamics is totally different. What happens in that case? And I think that just leads us to, how should humans actually use models? And, we build the models, we make decisions at the end of the day based on the outputs potentially, but to what degree should we listen to them? And I feel like there's this spectrum of, you write down a model and you look at a few different scenarios for things and you say, okay, it could be this, so that scenario, and what would we do in that scenario, or what would we do in that scenario? That can be kind of limited, and there's also this full decision theoretic approach where you write down posteriors and then you sample over this entire space. That can be inappropriate in situations where you have absolutely no clue what's going on. So there's this kind of interesting framework I am really interested in that Sarah mentioned to me, called robust decision making. It's a kind of combination of these things where you explore lots of scenarios, but in a somewhat methodologically rigorous way that kind of charts a course between these two. You know, how else would we build better models if we, incorporated more stakeholders or included more objectives about what we wanted out of the system? All that is relevant to model-based decision making, and I'm curious to learn more about. So, I mean, that's it. Just wanted to finish by thanking everyone in the entire world for helping me get here. Thanks to my advisors, Jean Gabriel and Lara. Good practicing. And then I couldn't list literally everyone who has just been awesome to talk to and work with at the center, but I just listed people who have done at least one sort of side project with. And then here's our awesome lab. And also just thank you to the committee members for being patient with me and reviewing the work. I'm really grateful for it. That's it. Yeah, thanks.
Thank you very much, Erik, for a beautiful talk. We will be taking questions from the public and also people online. Please raise your hand and I will call on you if you want to ask a question, or you can just type it in the chat if you would rather just have us read it. So with this, Avi.
Thank you, Erik. This is an excellent talk. I have a question regarding the set selection strategies. So you use greedy strategy for all of them.
Yes.
Did you try different strategies for vaccination and sentinel? And I also wondered if the results you got for influence versus sentinel versus vaccination was contingent on maybe pool optimization on the end of greedy.
It's a great question. It's definitely a whole in all of it is in these optimization problems. How do you know you're actually getting the optimal set, or you're just getting the greedy optimal set? For those of you who don't know, Avi has a recent paper which is totally awesome to use algorithms to sort of improve. You can do better than greedy, so you certainly can. I don't know. It'd be a curious future step for how you could see whether the optimization really does make a difference. We definitely saw when we were looking at the sets and the order in which sets were picked, there seemed to be some greedy logic working its way into how the sets were constructed. So it's definitely a fair criticism. Yeah.
Yeah, great time. I was curious, you were talking a lot about model specification. I was curious, sorry if I missed this, graph uncertainty is the idea that you can just marginalize over networks, or sorry if I missed that.
Oh yeah, no, yeah, so I'll just I didn't actually sort of included with the decision theory stuff, you could say you could come up with some posterior over all of your model parameters. You have this quality that we just said it's just a quality of the seed set, but that was contingent on you specifying an infection rate and a graph, and the probability of an outcome given a certain graph, if it becomes conditional on the graph or the infection rate, both are sort of equal input parameters to the model, and yeah, if you assume that the loss function you care about is the loss in expected quality, if that's your loss function, you can show that the sort of Bayes optimal predictor is just the expected utility marginalizing over the graphs. So yeah. Yes.
So when you presented in the supercritical regime,
yeah,
it seemed like the outcomes for sentinel surveillance and vaccination were very similar.
Mm-hmm.
And it makes sense to me with vaccination, you want to break up your connector component into as many sub pieces as possible. But it seems like sentinel surveillance is a very different kind of problem, right? Where you may intuitively you kind of imagine like the nodes like with the highest cleanest centrality or something would be the ones, right? Like kind of like this information hubs of the network or something. Like why do those two things align so well?
Yeah, great question. Great question. Two things. One, they might not actually align as well as we think. I'm just saying, like, for how different these influence maximization is as a problem, that you want to pick kind of the opposite of important nodes in a weird way. That could be just sort of skewing the color scale, if you will. So that we might say, okay, yeah, they are quite similar, but they are still different. Like there is some orange as opposed to bright yellow in that plot. But it's also not super straightforward in terms of sentinels, because you have first of all, you have lots of them, and we're weighting the problem based on you have to penalize sentinels that don't pick up the outbreak at all. So when there's an outbreak, you don't detect it at all. You have to penalize it somehow, and the way you penalize it is by taking the end time of the outbreak. So if there's a really small outbreak that happens on the system, you don't. If there's a really small outbreak that happens on the system, you won't be penalized for missing that so much, and so you're kind of strewn away from the periphery of the network. And I don't know if betweenness is like the right or wrong way to think about that, but it's not super obvious just based on structural features. There's kind of like some nuances to how you optimize. Yeah. That.
To Sam first.
Yeah.
I was curious about the miscounting or the overcounting methods by the message passing, and like, so in the end, if I'm deciding what strategy to use in order to immunize nodes, what I really care about is which one is better than the other, not necessarily exactly how much better. So are they overcounting in a way that is consistent between the different strategies they're immunizing? And if not, like which ones make it weirder?
Great question. Great question. And that is, that's something we looked at here. This is like, if you imagine that plot of message passing versus simulation, correlation between those two rankings, right? You have the ranking according to simulation, the ranking according to message passing. If you use this Spearman correlation to look at it, the correlation is quite good, but weirdly, the ranking gets kind of skewed as you increase the neighborhood size in a way that's almost counterproductive. So depending on, I think there's more work to do to really figure out exactly where the overcounting occurs. Laurent has some stuff on like coordinates maybe that might matter, but yeah, it's definitely a bit of an interesting future thing to explore to figure out exactly why and where in the network. And it's all further complicated when you do interventions. You're doing interventions on specific parts of the network, which could also, you suddenly change the way it's overcounting by removing some loops in the network, but not others. And yeah, so it's a really good question that merits further looking at.
Nicholas?
So if I understood correctly, a lot, or the models that you considered require a single exposure for contagion to spread.
Uh-huh.
And I'm curious, like, if you had something like a complex contagion process, would that be amenable to the approach? Like, how hard would it make it to use your analysis on that type of approach?
Well, it's interesting. For influence maximization, you are explicitly picking a number of nodes to be the seeds of the contagion. So for that problem, complex contagions would, I think, be the same. For surveillance, and I don't know. I feel like I don't know how complex contagions work well enough, and I I'm sure they can be sensitive to the initial conditions. So I guess you just need some way of defining a random set of initial conditions for the complex contagion. And if you can do that, then I think it would all work in the same way.
Yes.
So I don't know enough about message passing, but my question, sort of piggybacks off of Nick's. How well do you think message passing might generalize to other contagion processes on network? Because I feel like this one is very specific to independent, especially.
To the independent cascade?
Yeah.
Yeah, message passing does work for, there's a paper doing it for SAR processes, in continuous time. And, that's good. There's also a paper doing it for complex contagions, and it's really great paper. It's super interesting. You read all the way to the end, and at the bottom it says, "Oh, by the way, these aren't computationally tractable." I wish that had been like at the top. I spent all this time, but yeah, I think it's definitely an interesting tool. Mean field models in general. I mean, I think a big computational shortcoming of exploring this model misspecification type stuff is you have to go over the entire parameter space, and it's computationally challenging. So if you had a mean field model that works well, or I guess, there are these machine learning methods that can just sort of interpolate different parameters and other models. Yeah, computational improvements like message passing could potentially work well. Yeah.
Okay.
I can stop, so.
By the grad college rule, we're supposed to take questions as long as they come.
You could keep us here
That
forever.
rule is debated now. Okay, we'll take one last from Sam.
What about, like other types of model misspecification? Like, what if you wanted to see, like, what is the best model for avoiding going over some threshold of outbreaks, for example?
Yeah. Yeah, it all comes down to the utility function. And what I'm not going to be able to get to it, but yeah, that utility function, how you define it, you could just say terrible, like really, really punishing if your outbreak size is over 20 and then less. And actually, so that's something I really want to do is just take like the square of the outbreak size, or put a threshold and see how this sensitivity would change if you did that. And actually, with this Newman-Zipf algorithm we have, you don't require any extra computation. It's pretty much free. So yeah, definitely excited to try that. Thanks.
We have no more questions online either, except James Delk. We'll keep them until you see him in Burnham.
Great.
So with that, thank you again for the talk and the questions.
Yeah.
Stop the recording and ask the public to leave.